better method to add together vectors is called the analytical method. Now this is more precise in that it doesn't depend on your drawing skills and your getting the lengths correctly or the angles correctly when you measure vectors graphically. Now graphical method is a valid method and it helps, and we'll be doing a lab on it, and it helps to get a feeling for what the resultant vector should be. However, analytical method's more precise, actually gives you numbers and angles out. But to do the analytical method, what we need to do is break each vector down into its x, y, and if you're doing three-dimensional motion, which we will be ignoring for now, z components. Break them down into their x and y components and then add all of those components individually. So if you have three vectors, break each vector down into their x components, break each vector down into the y components, and break each vector down into the z components, and then add those up individually. So, again, we're just going to be dealing with x and y in this class. So here we have an example. There's an xy coordinate system. Again, positive x to the right, negative x to the left, positive y up, negative y down. The black vector here represents vector A. I want to break vector A up into its coordinates, into its components. So vector A has some component along the x-axis. So think of a flashlight shining down on this vector. What shadow does it make with the x-axis? If the vector is pointing directly up, there's no shadow. It has no x component. If it's horizontal, if the vector is pointing horizontally, all of the component is along. The shadow is just as long as the vector is. Here, the shadow is some length. That length depends on how long vector A is, so the magnitude of vector A, and the angle theta. So just using simple geometry, right, simple trigonometry, we can look at the length a sub x of this vector down here is the magnitude of A times the cosine of that angle theta. Likewise, the y component, imagine a flashlight shining from the right to the left. The shadow of this vector on the wall is the y component. That depends on the sine of theta. But you're like, well, the sine of theta is this opposite side here, right? If this is a right triangle, and it is, that's the opposite length. We can see that this length is the same as that length. So you can use trigonometry, sines and cosines, to break up the vectors into their components. Two caveats to this. The first is angle theta might not be given from the x-axis. Maybe theta, you're given theta, and say theta is so many degrees from due north. Say 30 degrees from due north. Well, then clearly, a sub y is now the adjacent side, so that should be the cosine. And a sub x is the opposite side, so that should be sine. So the equations I give you here are for measuring theta from the x-axis. If theta is not measured from the positive x-axis, you will have to go and make sure the trigonometry works. And all of you should be comfortable with sines, cosines, and tangents. If you're not, please send me a note, and I will send you a link that explains them in better detail. Second caveat is the sine. Now, this a sub x is pointing in the positive x direction, so this a sub x should have a positive sign to it. A sub y is pointing in the positive y direction. A sub y should have a positive sign to it. What if the vector isn't pointing in the first quadrant here? What if it's in the second quadrant? Let's look at this vector b. And let's use the angle we're given. Let's say we're given this angle, theta. Well, b has some x component, b sub x. And it has some y component, b sub y. Or the a sub y here for now. That's b sub y. Well, the y component is the opposite to the angle, so it's the opposite sign, so it should be sine, which is the same thing we have here, b sub y. B sub x is the adjacent side, so it should be cosine, which is the same as a sub x here. But note that b sub x is pointing in the negative x direction. So b sub x, you'll have to go in and put a little negative sign in front of it. Whatever value you get, if it's 10 or 20 or 30, it has to be negative because it's going in the negative direction. B sub y, though, is still going in the positive direction. So you have positive value there. So in the first quadrant, x and y will be positive. In the second quadrant, x will be negative, y will be positive. If the vector's in the third quadrant, both components are negative. If the vector's in the fourth quadrant, then x is positive, y is negative. And hopefully you'll be able to see that through the math on which direction the components are pointing. So after you break the vectors down into components, go back and make sure, depending on how you define your coordinate system, that everything pointing in the positive direction is positive and every component pointing in the negative direction is negative. Now your book gives many examples, and I'm going to do examples similar to what your book shows about sort of combining the head-to-tail method and the analytical method to show how they work in conjunction. So I have two vectors here, a and b. So vector equation I'm looking at basically is vector c is vector a plus vector b. So I added them head-to-tail method, right? So you have, starting at the origin, vector a, the end of vector a starts b, where you end here, that is vector c. That combination is vector c. So that's the head-to-tail method. Now the component method basically states that vector a has some value here, which is a sub x, and that's the length of a sub x. And it has some y component, a sub y. Vector b, starting at this point, has some component b sub x, which is that length, and some component b sub y, which is in this direction. And breaking them up into components, c sub x should be a sub x plus b sub x. C sub y should be a sub y plus b sub y. So a sub x plus b sub x is c sub x. That's the length that vector c should be. And you can see that, indeed, that is the length of vector c in the x direction. A sub y plus b sub y is c sub y, which you can see is the length of vector c. Now the advantage, again, of the analytical method is if I give you lengths and angles, you could quantitatively tell me what the components are, a sub x, a sub y, b sub x, b sub y, and then add those together to tell me what c sub x and c sub y are. And then if you wanted the total length of vector c, just remember Pythagorean theorem, the total length of vector c is equal to the square root of c sub x squared plus c sub y squared. Right, Pythagorean theorem.